Dear all, I am Dr. V. Malati, Associate Professor, EC Department, SR University, Warangal. So today's video lecture is on blood glucose level measurement using biosensor. After simulation, we will get glucose biosensor calibration curve. It's a graph of glucose concentration in milligram per dl versus sensor current in microampere. It will take the various data from sensor and then it is marked in the graph. And then we get dynamic response of glucose biosensor. It's a graph of time in second versus sensor current in microampere. So I have written the code in Python. I am going to simulate in Google Colab platform. Now I am sharing the screen. So now we got the output glucose concentration versus sensor current in microampere. So these blue dots represent sensor data. It is called as glucose biosensor calibration curve. And then calibration equation we have here is current in microampere is equal to 0.799 multiplied by glucose in milligram per dl plus 2.236. So unknown sample measurement measured current is equal to 150 microampere. Estimated glucose level is equal to 184.95 milligram per dl. So one more graph, a dynamic response of the glucose biosensor. It is represented time in second in x-axis and then sensor current in microampere. Now I am going to explain the wave code line by line. So it is the electrochemical glucose sensor simulation. So first one and then already I told you current in microampere, that is calibration equation, and then unknown sample measurement, it will give the estimated glucose level. So, okay, now this experiment simulates a glucose oxidase, that is GOX, that is electrochemical biosensor, where glucose reacts with enzyme. It produces H2O2. That H2O2 is the oxidation generation which is generating the current. Then generated current is proportional to the glucose concentration. Now this current explains calibration curve, which is showing linear relationship between glucose concentration in milligram per dl and then sensor output current in microampere. Then linear regression, it finds calibration equation, that is I equal to mc plus b, where I is the current, then C is the glucose concentration, M is the sensitivity, then B is the baseline current. So unknown sample estimation. How it is done? It uses inverse calibration equation to estimate glucose level and then dynamic response. It shows exponential response behavior of biosensor. Then expected output we get is calibration curve graph, calibration equation, then estimated glucose value, then dynamic response plot. This program simulates how an electrochemical glucose biosensor works. In real life, glucose reacts with glucose oxidase enzyme and then a reaction produces electrons. These electrons generate a measurable current. Current is proportional to glucose concentration. The code models this process mathematically. Now we import required libraries. First one, import numpy as np. Import matplotlib.pyplot as plt. Then from sklearn dot linear underscore model import linear regression. Now we explain line by line. NumP, it is used for, that is NP, it is used for numerical calculations, arrays, then random noise generation, then matplotlib. It is used for plotting graphs, that is calibration curve and response curve. Then linear regression. It is used to find best fit line, that is calibration equation. Then sensor parameters. Sensitivity is equal to 0.8, that is microampere per milligram per dl. Then baseline underscore current is equal to 2, that is microampere background current. Noise underscore level, it is equal to 0.5, that is noise in microampere. Now we see line by line explanations. These simulate real biosensor characteristics. First one, sensitivity. It is 0.8 microampere current per 1 milligram per dl glucose. Then higher sensitivity, it will give more responsive sensor. Then baseline current. Even with no glucose, sensor shows smaller background current due to electrodes and electronics. Then noise level. Real sensors have noise. It is 0.5 microampere random fluctuations added. Then generate glucose samples. Glucose underscore concentration, it is equal to NP dot linspace open bracket 50, 300, 20, that is milligram per dl range, and this line creates 20 glucose values between 50 milligram per dl, which is lower target level, and then 300 milligram per dl, that is higher level. This simulates lab calibration samples. Now sensor current simulation. Sensor underscore current is equal to sensitivity into glucose underscore concentration plus baseline underscore current plus NP dot random dot normal open bracket 0 comma noise underscore level comma LVN glucose underscore concentration. This is the most important equation. The formula used here is I equal to SC plus I baseline plus noise, where I equal to sensor current and S is sensitivity, and then C equal to glucose concentration and NP dot random dot normal open bracket 0 comma noise underscore level comma it is the size. So it adds random measurement noise. Then plot calibration curve. PLT dot, so it is the PLT dot figure. The figure size is equal to 8 comma 6. So 8 is the width, 6 is the height. Then PLT dot scatter open bracket glucose underscore concentration comma sensor underscore current, and this shows glucose in milligram per dl. It gives a current in microampere. If sensor works properly, then it points from a straight line. Slight scatter due to noise. This is the calibration curve used in real biosensor labs. Then linear regression. It is also calibration equation, and it is reshaping the data. And then X is equal to glucose underscore concentration dot reshape open bracket -1 comma 1, Y equal to sensor underscore current dot reshape, then -1 comma 1. Machine learning models require 2D input. So reshape open bracket -1 comma 1 converts 1D array to column format. Then fit model. So model is equal to linear regression open bracket close bracket model dot fit open bracket x comma y. This calculates best fit straight line, that is I equal to MC plus B, where M equal to model coefficient. It is giving the sensitivity. Then B equal to model dot intercept underscore. It gives baseline current. Then print calibration equation. So current in microampere, it is equal to M into glucose in mg per dl plus B. This is exactly how real glucometers are calibrated and predict unknown sample. Unknown underscore current, it is equal to 150. So suppose sensor measures 150 microampere. We reverse the equation C equal to I minus P whole divided by M. This estimates blood glucose level. This is how glucometers calculate glucose from measured current. Dynamic time response simulation. It simulates 10 seconds of measurement. Step input. Then step underscore glucose is equal to 120. Suddenly glucose becomes 120 milligram per dl. It is exponential sensor response. It will give exponential sensor response. Now, sensor underscore current is equal to sensitivity into step underscore glucose into open bracket 1 minus np dot exponential minus time by 2 plus baseline underscore current. Now, this line models real biosensor behavior, and the term 1 minus e power minus t by t, it represents slow rise and then time constant equal to 2 seconds and then gradual stabilization. Real biosensors do not respond instantly. So final plot shows time in seconds versus current in microampere. You will observe exponential rise, then steady state after few seconds. What this experiment teaches? In this section, sensor parameters, what concept we have, biosensor characteristics. Next, calibration curve. From this, current versus glucose relationship. Then linear regression. It finds calibration equation. Then unknown prediction. It gives glucometer working principle. Then time response, the dynamic sensor behavior, and then complete mathematical model used. Static model, that is I equal to SC plus I naught plus noise. Then inverse model C equal to I minus I naught by S. Then dynamic model I of t is equal to SC open bracket 1 minus e power minus t by t plus I naught. So in this way we can measure the glucose level. So the waveform, it is glucose biosensor calibration curve, and the sensor output data is taken and marked with glucose concentration in x-axis and then sensor current in microampere. So this is the form of the graph we obtained. And the calibration curve, that is calibration equation, that is current in microampere, it is standard formula decided, it is equal to 0.799 into glucose in terms of milligram per dl plus 2.236. For unknown sample measurement, the current is 150 microampere. The estimated glucose level is equal to 184.95 milligram per dl. And this is another one, dynamic response of glucose biosensor. It shows time in second versus sensor current in microampere. So here it simulates a glucose oxidase, that is GOX. It is electrochemical biosensor. So glucose reacts with enzyme and it will produce H2O2. This H2O2 oxidation generates current, and that generated current is directly proportional to the glucose concentration. So the calibration curve shows the linear relationship between glucose concentration in milligram per dl versus sensor output current in microampere. Then linear regression finds calibration equation, that is I equal to mc plus b, where I equal to current, C equal to glucose concentration, M equal to sensitivity, D equal to baseline current, and our sample estimation is done by using the inverse calibration equation for estimating the glucose level, and we get dynamic response showing exponential response behavior of biosensor. So we will get calibration curve graph, then calibration equation, estimated glucose value, then dynamic response plot. This program simulates how an electrochemical glucose biosensor works. In real life, glucose reacts with glucose oxidase enzyme. This reaction produces electrons, and electrons generate a measurable current, and this current is proportional to glucose concentration, and this models the process mathematically. Importing required libraries, that is import Napiers NP and then import matplotlib .pyplot as PLT. So we are using NumPy for numerical calculations, arrays, random noise generation, and matplotlib is used to plot graphs, that is calibration curve and response curve. We use linear regression. It is finding the best fit line, that is calibration equation, and already we got the sensor parameters. Sensitivity is equal to 0.8. So it is microampere per milligram per dl, and then baseline underscore current. It is equal to 2 microampere, that is background current. Noise underscore level. It is equal to 0.5, that is noise in microampere. These simulate real biosensor characteristics, that is sensitivity means 0.8 microampere per 1 microampere current per 1 milligram per dl of glucose. Then high sensitivity indicates more responsive sensor. Baseline current. So even with no glucose, sensor shows small background current due to electrode and electronics, and then noise level Real sensors have noise. 0.5 microampere random fluctuations added and generate glucose samples. Glucose underscore concentration is equal to NP dot linspace open bracket 50 comma 300 comma 20, that is milligram per dl range. It creates 20 glucose values between that is 50 milligram per dl, which is lower range, and 300 milligram per dl, which is higher range. So in the step of 20, the simulates lab calibration samples. Then sensor current simulation. Sensor current is equal to sensitivity into glucose underscore concentration in plus a baseline current underscore current plus NP dot random dot normal open bracket 0 comma noise underscore level comma LEN glucose concentration, and this is considered to be a most important equation, and the formula simply we can write I equal to SC plus I baseline plus noise. So I means sensor current, S means sensitivity, C means glucose concentration. So NP dot random dot normal 0 comma noise level comma, and this is the indication of size. So it adds random measurement noise. Plot calibration curve. Plot that is it produces the figures with the size of 8 width 6 height. So plot dot scatter glucose underscore concentration comma sensor underscore current. So this shows glucose in milligram per dl. It gives the current in microampere. If sensor works properly, it points from a straight line. Slight scatter due to noise. This is the calibration curve used in real biosensor labs. Then linear regression calibration equation. So it is reshaping the data. X is equal to glucose underscore concentration dot reshape open bracket -1 comma 1. Then y equal to sensor underscore current dot reshape open bracket -1 comma 1. Machine learning models require 2D input. Therefore, reshape open bracket -1 comma 1 converts 1D array to column format. Then fit model. So model equal to linear regression open bracket close bracket. Model dot fit open bracket x comma y. This calculates best fit straight line, that is I equal to MC plus D, where M equal to model coefficient and it shows the sensitivity. Then B equal to model dot intercept. It gives the baseline current. Then we have to print the calibration equation. Current in microampere. It is equal to M into glucose milligram per dl plus B. This is exactly how real glucometers are calibrated. Then predict unknown sample. So unknown current is equal to 150. Suppose sensor measures 150 microampere. We have to reverse the equation. C equal to I minus B by N. So predicted glucose is equal to unknown current minus intercept divided by it is the slope. So this estimates the blood glucose level. So with this we conclude the explanation. Thank you.